welcome to Sunday's edition of Cracking the Cryptic, where we're going to be having a look at a puzzle called Central Tendency by Pixel Plucker, no less. Pixel Plucker is an absolutely brilliant setter and solver, I might add. And this is just a normal killer Sudoku today, which is a rarity indeed on the channel. Let's have a quick look at it. We've got a T-pentomino there, and some dinosaurs facing off in the top of the grid. Look, that's definitely a T-Rex or a Velociraptor, and this is another one. So I don't know what's going on with this. I have left it incredibly late today to record a video, so I'm under some pressure to get this done with some sort of alacrity. I'll read you the rules in just a second for those of you unfamiliar with Killer Sudoku. The first thing I need to do, though, of course, today is to read out the names. We've got more successful solvers of the Star Wars Sudoku Hunt, which is available over on Patreon right now. If you're a patron of the channel, check it out. You will not regret it. The plaudits that Peter C Hayward has been getting for this hunt are, well, legion. And well done to Alan Bagg, to Dean and Orion, to Jamie Stearns, to Ryan Fitzpatrick, Amy Lacus, and Awesome Source 21. All of you have correctly identified the name of the next trilogy, so very, very well done. And you've still got, if you haven't had a go at it yet, you've still got till the 20th to get us a correct solution in and be eligible for a prize. Now, let's get on with the rules of Central Tendency. I wonder why it's called Central Tendency. I suppose I get a given digit in the centre. I don't really understand that, though. Someone can explain it to me in the comments. And the rules are as follows. Normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage if given. Hang on a moment. Oh, yeah, that cage does not have a total. Well, the final part of the rules is that digits cannot repeat within a cage. So all we actually know about this cage is that it doesn't have a repeated digit in it, which is really weird. That suggests, well, I shouldn't say this because it might be relevant to the solve. It suggests this cell is quite important, doesn't it? Although it could be the fact that actually now I look at it, this puzzle has rather beautiful symmetry, doesn't it, around the central column. We've got the dinosaurs facing off against each other, but we've also got every single other cage pattern is symmetrically disposed, so that's rather gorgeous, and the sign of class setting indeed. Do have a go at the puzzle. The way to play is to click the link under the video as usual, and now I get to play. Let's get cracking. Now, let's get cracking. Do we need to use the secret, I'm wondering? The secret, and I only tell this to my very favourite people, is that any complete box of a Sudoku will, if correctly completed, contain all of the digits 1 to 9 exactly once each. And the digits 1 to 9 add up to 45. That's the secret, because it allows us to do maths so often. So, for example, in box 7 here, we've got an 18 cage and a 13 cage. So I know that those 6 cells add up to 31. Now, 45 minus 31 is 14. So I know those 3 cells add up to 14. And you're quite right if you're saying, yes, Simon, but that's useless. It is useless, but it might not have been if these had been a bit bigger. We've got something similar going on there. Look, we've got 32 into those squares, so those 3 add up to 13. We've got, don't know actually. Oh, 12 and 17? No, that's not big enough either. Maybe this is why it's called Central Tendency, because everything's sort of average. We've got the dinosaurs, which are 29 summed in 6 cells. Oh no, that's horrible. That's horrible. So one way of viewing the dinosaurs is that they are missing 3 cells that add up to 16. Because of course a 9-cell cage would contain all of the digits from 1 to 9 and would add up to 45. So a 6-cell sum to 29 is missing 3 cells summing to 16. And they're both missing 3 cells summing to 16. Okay, so maybe Okay. Is that true? Is what I'm about to say true? Yes, I think it is true. Yeah, okay. I think actually what we've got to look at is this domino here, believe it or not. So the start of this puzzle might be this 10 cage. And I suppose by symmetry, that 9 cage. Because what I'm thinking is that whatever digits we populate this 10 cage with, those digits cannot appear anywhere in our velociraptor here, because these cells see the entirety of the 29 cage. And the same is true here, but with a 9 cage. This 9 cage sees the whole of that velociraptor. Now that means that those 8 cells there are all different digits. And we know their sum. Their sum is 29 plus 10, which is 39. So if these 8 cells are all different, and they add up to 39, what can they not have in them? And the answer to that is 6, because we know that 45 minus 39 is 6, and if there was a 6 in there, that would sort of break the rules of mathematics. So that means 6 in box 1 is in one of 2 places, which is, that's really very beautiful actually. I like that a lot. It's sort of a virtual 39 cage. Okay, so let's do the same over here then. Sorry, I was just trying to see if that meant anything. So that's a virtual 38 cage. So that's missing a 7. So there must be a 7 in one of those 2 cells. Okay, don't know what that's doing. Is that doing something to the 17 cage now? So the 17 cage can't have a 6 in it, and it can't have a 7 in it. So it's got to have... Well, it can't have an 8 and a 9 in it, because although Sven's marvellous software will allow us to do something like this, the rules of Sudoku won't. So there's either a 9 or an 8 in the 17 cage, and we know that because 5 plus 4 plus 3 only add up to 12. So if there's a 9 in there, the other 2... Oh, yeah, actually that might be interesting. So if there's a 9 in the 17 cage, the other 2 digits will add up to 8, and will have to be 3 and 5 only. Now what about if there's 8 in there? If there's 8 in there, the other 2 digits will add up to 9, and will have to be 4 and 5. Whoa. So... and that's never a 5 because of the given digit. Yes, here's something interesting. Right, this 12 cage at the top of the grid can't be 5, 7. So it's either 3, 9 or 4, 8. And look at that. That's a 3, 4, 5, 8, 9 quintuple in box 2. And an inverted T pentomino, looking up from that one, this one adds up to 29, that one adds up to 23. So these digits now have got to be 1, 2, 6 and 7 to complete this box. What does that mean? I don't know. That means that... I don't know. Well, we know there's no 6, don't we? We know there's no 6 in the 29 cage because we worked that out before. It's got to be missing a 6 because these cells added up to 39. So that's a 1, 2 or a 7. Ah, yeah, okay. Well, that's a little bit interesting. Let's bounce this 1, 2, 7 back into box 1 and ask where it goes. Because the teeth of the velociraptor here... Just as this 10 cage sees the whole of the velociraptor, the nose of the velociraptor sees the whole of the 10 cage and obviously can't repeat within its cage. So whatever this digit is must appear somewhere in box 1 and has to be in one of those 2 squares. So these 2 squares are either, well, there's definitely a 6 in them, and there is also going to be with this digit, whatever this digit is. So those 2 digits are relatively limited. Now this is in a 10 cage, so that can only be 8, 9 or 3, 4 now. That looks unhelpful. Let me just think about that. If... No, Pixel Plucker, you meanie. I don't think that is doing very much at all. let's come back over here and check this one. So we know that these added up to 38, so there was no 7 in them, so that's not a 7. And this, okay, oh yeah, look, we're going to get a quadruple in row 3. This is beautiful, good grief. Right, this, the nose or the teeth of this Velociraptor are a 1, 2 or a 6, and again, they can't repeat in those digits. So whatever's in here can't go in those 7 cells of box 3, because it'll repeat in its cage or repeat in its row. So these 2 squares are also from 1, 2, 6 or 7, because we know there's a 7 in one of them. And that's a quadruple now we've got in row 3. Which means that the gap cells, it's slightly excessive to do this, but pencil mark would approve of it. They've got to be 3s, 4s, 5s, 8s or 9s. And they're not 5s, because we know that the 5 in box 2 is in one of those 2 squares by our old friend Sudoku. So all of this has really done nothing. We've got this down to being, or these 2 squares down to being 3, 4, 8 and 9. Oh, and I've not filled in this 8 cage. That's 1, 7 or 2, 6, look. No, okay, goodness me. Well, what I can say is that this is fascinating, even though I haven't got a clue how to do it. So, can we... I'm tempted to try and use maths now. Is that a stupid idea? No, it's simple. No, I don't have to do maths. I'm not even sure if maths would work, but what can this digit definitely not be? Well, it can't be 7, because if it's 7, you have to put a 7 in one of those 2 squares, but you know in box 3 there's a 7 in one of those squares. So, yeah, this is better. This is a better way of thinking about the world. So this is definitely not a 7. In fact, if I'd push through my pencil marks further, you can see, because there's a 6 in one of those, then there cannot be a 6 in one of those, and because there cannot be a 6 in one of those, there cannot be a 6 here, because if there's a 6 here, we know that its only possible positions in box 3 would be one of those 2 squares, where it cannot go because of the 6's over there. So actually, this is a 1-2 pair, which means those 2 squares are not 1s and 2s. Now we've got a 6-7 pair. We're not even close to getting a digit, but we have done some quite beautiful logic that Pixel Plucker has somehow built or baked into his Velociraptor pie. I sort of want to check the maths on this. I know it should work, but let me just do this. We've got 2 lots of 29, that's 58, 68, 77, 77 plus 1, 2, 6 and 7 is 93. Yeah, that's beautiful. And we know that one box of a Sudoku adds up to 45, so that's 2 lots of 45, which means we must deduct 3 from that, because 2 lots of 45 is 90, and we know that we've got 93, so we need these to be 1 and 2 in order to restore parity to the universe and ensure that boxes 1 and 3 do indeed add up to 45 each. So now what do we do? Because that was... Oh, yes, I know what we do. Now I've got a 1-2 pair looking at that domino, and they can't have a 6 in it for the reasons we've mentioned ad nauseum. So that domino there can't be 1, 9, 2, 8 or 4, 6. It's got to be 3, 7. And now the 9 cage can't have a 1, 2 or a 3 in it. So that's 4 or 5. There's no 4 in this domino. There's no 3 in, not domino, there's no 4 in that cell. There's no 3 in this cell. Now 3 and 4 are ruled out of that square, so this is 8 or 9, which means this is a low digit. This is a 3 or a 4. Okay. So yeah, it's interesting. So whatever it is going to make a pair either with this domino or with this domino. If this is a 3, it pairs up over here and places a 3 there. If it's a 4, it pairs up over here and puts a 4 here. So these squares in row 1. Oh, yeah, okay. So what a sensible question to ask would be, where does the 6 go in row 1? Because it's not here, because of the 6 is there. So we've got an 8, 9 pair, and we can place 6, and that's our first digit. Our first digit is a 6. Ah, beautiful. Right, so this domino now, which used to be able to be 2, 6, can't now be 2, 6. That's got to be only 1, 7. Let's restore the 7 pencil mark into that square, because we know one of those 2 squares is a 7 in box 3. 1, 7 here. What's that doing? I'm tempted to try and do maths on this domino and this cell now. Is that a silly idea? What have we got here? We've got 16 and 25. That's 41. So that's telling us these squares have to be 4 greater than this square, I think. And the way to realise that is, of course, that this box adds to 45. So whatever we put in here is reducing 41 by this value. But we know we need to get, for the whole box, from 41 minus x back up to 45. So we're going to have to make sure these add up to 4 more than x. So, right, we're going to go full hand pencil mark then. So this square is 2, 3, 4, 5, 8 or 9. Actually, I'm not actually sure that this is a sensible thing to do. If that was 2, these would have to add up. Okay, if that's 2, I can rule 2 out of this square. If that's 2, this has to be a 1, 5 pair. Because these 2 need to add up to 6 for the reasons I just mentioned. Well, we can't put 7 in there, so we'd have to go 1, 5, and the 5 would clash. So that is not 2. If it's 3, we need these to add up. No, that doesn't. Yeah, if this is 3, this doesn't work either, because these have to add up to 7, which means 1, 6 is necessary. We've already got a 6 in the column. 4. No, 4. We need another 1, 7 here. This is gorgeous, because these have to add up to 8, and that won't work. So we've got this down to actually a reasonable number of options. If it's 5, these have to add up to 9. Oh, bobbins, that's blooming bar humbug. That's possible, isn't it? That's got to be either 8 then or 2. So if that's 8, these have to add up to 12. Oh, 12 doesn't work. Hang on. 8 here. No, that's interesting. 8 doesn't work either, because 8 here means we need these to add up to 12, so this has to be 7 and that has to be 5 again, which doesn't work. If we can get rid of 9, this is a very, very beautiful cell. 9 would require 30, no, hang on, what are we saying? 13, 4 different. Oh, good grief, that is so clever, wow, doesn't work. So I don't know how you have this sort of idea, but Pixel Plucker has worked out that if you put 1, 6 and 7 in a column and you set up this geometry with these cages, this square becomes a naked single effectively. It can only be a 5. That's so weird. So it's sort of the juxtaposition of the 1, 6 and 7 and the 5 in the middle all operating on this square. Yeah, if this is 9, these have to add up to 13, which requires 7 and 6, and the 6 would repeat. So that's a 5. Okay, so we know these add up to 9, but we don't know what version of 9 they are. They could still be 2, 7 or 1, 8. But at least we got another digit. And now we've got maths, have we, on box 9? We've got 37. These add up to 8, and they don't use 5. So that's not 3, 5. That's 1, 7 or 2, 6. You can't put 5 in the 23 cage now. I'm definitely going to record that. So 5. What about 5? Oh, look, yeah, okay. Where does 5 go? In box 6. It can't repeat in its cage. Can't go there by Sudoku. Can't go here by Sudoku. So there is a 5 in the 16 cage, along with 2 cells that add to 11. So they're not 5 and 6 anymore. Although I don't think... Oh, well, the corollary of that is if there's no 5-6 pair in the 16 cage, where's the 6 in this box? It's got to be in the 25 cage, and it's not here by Sudoku. So there's a 6 in one of 3 cells in the 25 cage. So now we've got 11 in the 25 cage. We need 3 cells that add up to 14, which don't repeat the 5 or the 6, but that doesn't seem very appetizing, I have to say. Okay, so now we're stuck. 6, 1, 7. Right, there's something going on with the 1-7 pair though. That's... Oh, God. Blimey, that is absolutely gorgeous. Wow. Okay, we're going to look at this domino because this is a 1-7 pair. So I want to ask where 1 and 7 go in box 9. And the answer on the face of it is not in those squares. What happens if you try to put one of those digits here? Let's try and make this a purple digit. Well, if it's a 1, this domino has to add up to 16 and it has to be a 7 and a 9 pair. That's the only way of doing that in 2 cells. It can't be a 7-9 pair. There's already a 7 in the column. So it's not a 1. What if it's a 7? And this is where it's so beautiful. If this is a 7, this domino adds up to 10. But it can't, because 1-9 isn't available. 2-8 is not available because of this cell. 3-7 isn't available and 4-6 isn't available. So this square cannot be purple. Now, can you put both purples into the 15 cage? And the answer is no, because if you put 1 and 7 in the 15 cage, you're going to have to put another 7 in there to make the 3 cells add up to 15. Now that tells us, at this point, that there is not a 1 and a 7 in the 15 cage. Therefore, one of these digits must be purple. But once one of them is purple, because they add up to 8, the other one is also purple. So they are both purple, and they are therefore a 1-7 pair. And that is just, I mean, that's sublime. I was wondering if I was going to get a 1-7 pair in column 9, but apparently not. So, what is that telling us about the price of bread? Is it telling us something? That must be deliberate. I mean, that's too beautiful. It's too set up. You know, the selection of these totals and the way it works with especially with that cell. That's too deliberate for this not to matter. So 9, 2, 4, 8. Oh yeah, this puzzle is class. It is class in a glass. Let us look at the 15 cage now. Now the 15 cage needs a high digit in it, by which I mean an 8 or a 9. If it doesn't have an 8 or a 9 in it, the maximum you could put into those 3 squares would be 6, 4 and 3, and they don't add up to 15. So we know that there's exactly one high digit. Well, if that high digit is a 9, what do we pair it up with? 2 digits that add up to 6 that don't include a 1. So that's got to be 9, 2, 4. But if there's an 8 in here instead, then we need 7 more that aren't 1, 6 or 2, 5. In other words, they're 3 and 4. So what we learn about this cage is it has a 4 in it. And if this cage has a 4 in it, and there's some 4s up there aligned in columns 8 and 9, we should be asking the question where the 4 goes in column 7 of the grid. because it can't be in those three and it can't be in those three. It can't be in that one or that one, so it can only go there. That is a 4 out of absolutely nowhere. Ah, no. Well, yes. No, yes. No, the other question I should be asking, and perhaps this is a simpler question, is where does 6 go in this box? Because it's not in that 15 cage, so it's got to go there. So that's a 6. Those are adding up to 11. And they are not 5, 6 or 4, 7. So these squares are either 3, 8 or 2, 9, which is... Oh, okay. No, perhaps that's not interesting. That's the same then. That's 2, 3 or 8, 9. So these add up to 11 and those two add up to 11. Oh, yeah. That is important. If these two add up to 11... which they do, because they're whatever. If this is 2, 9, this is a 3, 8 pair, then we can actually restrict the value of this. That is not an 8 or a 2, it's a 3 or a 9. Yeah, nearly interesting. I don't know if I can do anything with that. I'm not sure. Oh, 6. 6 in box 6 is now fixed into that cell. So we've now got 15, or 3 digits adding to 15 in my 25 cage. So these two cells add up to 10, and they're not 4, 6. That's about all we can say about those. They could be 1, 9, oh they can't be 2, 8 of course. Right, okay, so these are 1, 9 or 3, 7. Ah, that's almost perfect, but unfortunately these digits have let themselves down and it's not perfect. The other, we need 2 digits that sum to 11 in there. Oh, the 14 cage can't have 4, 5 or 6 in it now. Whoa, what can that be then? Wow, okay, so that's really interesting. It can't have a 7 in it. If you put a 7 in it, the other 2 digits have to add up to 7 and would have to be 1, 6, 2, 5 or 3, 4, all of which are ruled out. So this has got an 8 or a 9 in it. It's not got an 8 in it, because if it's got an 8 in it, the other domino adds to 1, 5 or 2, 4, both of which are ruled out. So I think that's got a 9 in it, along with 2 cells that sum to 5 that aren't 1, 4. So that's 2, 3, 9 out of absolutely nowhere. This square is not 3 or 9. This square now is not 1 or 7, because we know those added up to 10. Oh, now I've got a 1, 7 pair in the column. Good grief. And a 1, 7 pair in the box. So... oh no, okay, no, it still doesn't do it. I was thinking that was going to give me my 16 cage. No, it doesn't. These two, what we now know is these two add up to 11 as well. Oh, that's weird. So these two add up to 11, and whatever they aren't ends up in the 16 cage instead. Good grief. This is stunning, though. It's absolutely stunning. 28 minutes this take. That has flown by. Good lord. If you'd have said I was 15 minutes into it, I'd have gone, no, I'm probably not. No, I'm about 12 minutes. Done about 12 minutes of logic so far. It's a sign of a good puzzle. And, well, yes, it's a sign of a good puzzle, and this is a great puzzle, but it's also the sign of a puzzle that has completely involved my brain. So in this row, we need 1s, 5s, 7s and 8s into these squares. 1, 5, 7 and 8. So there's definitely, because 5 and 8 have to be over this side, look, in this box, that square is not an 8, which means that square is not a 2, so this is down to 1 or 6. Hang on, why has this got 3? Why has this got 3 options and this has only got 2 options? Let me just go back, hang on. Oh, this had... why have I done that? Oh, I think maybe I filled this in when I thought it could be a 7, because I seem to have put a 3 in there. That definitely isn't possible. So that's not 3, because that can't be 7. And now this can't be 8, so this is down to just, well, 1 or 6. Okay, and this is 4 or 9. But you can't put 5 or 8 in the 17 gauge. Does that matter? Does that mean it has to have 9 in it? It might do. I'm not sure actually. If it's not got 9 in it, how would you make it up? It would have to be no 9s, no 8s, 6, 7. Oh no, 6, 7, 6, 7, 4 would work, wouldn't it? 6, 7, and 4. They do add up to 17. Sorry, I'm not. I feel like this is the natural place to look because we have got a restriction on the 17 gauge. It can't have 5 or 8 into it. But I don't understand what the point of that is. It can still have 2 in it. It could be, yes, it could be 2, 6, 9. Oh no, it can't. Ah, right, that's it. That's the point of this. Right, that's beautiful. Okay, 5 and 8 are not available for the 17 gauge. So the question I want to ask is there a 3 in the 17 gauge? I don't think there can be, because if there's a 3 in it, the other 2 digits have to add up to 14, which means they're either 5 and 9, well they're not that, or they're 8 and 6, well they're not that either. There's no 3 in there. So 3 is in... Oh, this is beautiful. Good grief. Right, so 3 is in this domino, which means that square's a 9. These had to add up to 10, didn't they? So that's a 1. I'm just going to double check the maths. Yeah, that adds up to 25. 1 gives me a 7. It gives me a 1. Oh, beautiful. Gives me a 6 over here and a 4. Gives me a 2. Gives me a 7. Gives me... They had to add up to 4 more than 5 now. Yeah, so when that's 7, that becomes 2. There's no 2 down here. They were pairing, the 2s were pairing up with 9, so this is a 3-8 pair. That means that's a 9 in box number 3. Don't know what that means. We can now eliminate 3 and 8 from this cage. So this 15 cage is now 2, 4, and 9, and that's not 9. 4 and 9, and the 16 cage here is 3, 5, and 8. Oh, and there's 3 and 5 looking at that square, so that's an 8. That's a 3, 5 pair. I'm not sure if we can improve on that. 1 here means we get a 1 and a 7 at the bottom of the grid. Okay, and what are we looking for here? 2s, whoopsie, 2s, 3s and 8s, I think, to complete this box. I don't know if we can do anything with that. We probably can, but I can't see how to do it. Okay, let's take stock. Can we do more Sudoku? That's a good question for me especially to ask myself. I don't think I can on this side of the grid. Which almost certainly means, yes, of course we can, but I can't now. I'm not sure. We might be able to, but I can't see how to do it. So what have we just learned from this activity? Now, okay, now we know there is a 2 in my 17 cage, and we know where the 2 goes, just by Sudoku. Where does 2 go in that box? It goes here. So these 2 squares add up to 15 and don't involve an 8, so they are 6 and 9. Lovely, so we actually get more digits this side of the grid. 1 comes out of those squares, so this little triple is 5, 7 and 8 now. These 2 squares are 1 and 3, which means that 2 is in one of 3 places in column 3. These squares are now known. They are 1, 6 and 8, which doesn't seem to be helpful. And those squares are known, and they are 4 and something, 7. So 7 is now aligning, look, in boxes 2 and 5. So where does 7 go in column 5? In none of those 6 cells. So we've got a 7 in one of 2 places down here. We've got, I don't know what else we've got. We've got something else, I'm sure. We've got, we've got a funny cage that doesn't have any. Ooh, that square is rather interesting. Look at this square. This has very few options because look, it sees this is quality. I love this. Look at this square and look at this 1-3 pair, which ordinarily this square could not see. It would see this one by Sudoku, but it wouldn't see that one. But because of the shape of the cage, it sees both of those digits. So this can't be a 1 or a 3 or a 4 or a 6 or a 5 or a 7 or an 8 because it sees all those things. So it must be a 2 or a 9, I think, only. That might be wrong. I'm just going to double check that. 2, 5, 6. No, it's not wrong. 2 or 9. That's a 2, 4, 9 triple in the row. Is that doing something I'm not understanding? Probably. Sorry, I'm not seeing what that's doing. 2, 4, 9 triple in the row. So I need 1s, 3s, 6s, 7s and 8s. 1, 3, 6, 7, 8. 3, 6, 7, 8. Is that supposed to be ringing any bells with me? 1, 3, 6, 7, 8. But I don't think we know anything about any of these possible digits, do we? I'm not sure. Sorry, I'm not seeing how to do that. T pentomino, we've got a 7 in it. So the other 4 digits have to add up to 16, but they don't use a 5. So does that mean we have to have an 8 or a 9 in it? If we don't have an 8 or a 9 in it, we'd be looking at 6, 4, 3, 2, which is 15. That's not enough, right? So we need to accompany this 7 with either a 9 or an 8, not both, because they'd add up to more than 16. So if we've got 9 and 7 in here, the other digits would be 1, 2 and 4. Would actually be quite restricted. In fact, that would be really restricted with this 2, 4, 9 gubbins we've got going on. 9, 7, 1, 2, 4. Yeah, that wouldn't work. That might be it, actually. If this 23 cage is made up of 9, well, let's do it in order. 1, 2, 4, 7, 9. Then because of the 2, 4, 9 triple, these 2 squares would have to be filled with the digits 2, 4 and 9. And that's impossible. You can't get sort of double Schrodinger cells down here. So this has not got a 9 in it, so it must have an 8 in it, is what I'm alleging. And if it's got an 8 and a 7 in it, the other 3 digits are adding up to 8 and don't have a 5. So it's got 1, 3, 4, 7, 8 is, I think, what we've got in there. 1, 3, 4, 7, 8. And we can get rid of the 4 from this row because we've got the 4 over here. 3, 4. We can get rid of the 7 from everywhere other than where the 7 is in the box, because we know the 7 is in one of those 2 squares. And now maybe we look at what goes in these other squares, therefore. We've got to put 2s, 4s, 5s and 9s in. No, we don't. That does nothing. Oh, good grief. Is that really true? Or have I dropped the ball there? If this is... Okay, we know that there's a 4. Yes, I have dropped the ball. There's definitely a 4 in this 23 cage, and we know the 4 is vertical now. So it's looking upwards at this little square. Wow, so that's a 3, and that's a 9, and that's an 8. So 9 comes out of there, and 3 comes out of there. So this is now 4, 5, 8, and that becomes a 3. Good Lord. And that square is presumably now known to be a 9. Ooh, that's looking interesting. So 9 is in one of those 3 squares along with 2. And what you can't, we know that already, what you can't do is pair up the 9 and the 2 in the 13 cage because you'll need another 2. But that's exactly what this digit is already telling us. Bother. Okay. 3 and 9 here, looking at that square, so that's got to be a 2. Which means what then? The answer is I don't know. Bother. Bother. Okay. Oh, I know what I might be able to do though. Do I now know what that digit is? Yes, I do. Of course I know what that digit is. I've probably known what that digit is for about half an hour. Because that digit had to appear in one of those 2 digits in box 3. So that digit's a 1. That digit's a 2. So those are not 2s. This is not a 1. That's done nothing either. Good grief. This is not an easy puzzle. It really isn't an easy puzzle. At least I don't think it is. Okay, so what do we do now? We're going to have to work on the 2, 5. So we need 1s. That's not 4, is it? Because the 4 was down there. So we can get rid of 8. We can get rid of 4 from here and we get an 8. So now we're on to... We've managed to lock this down to a 4, 5 pair. We've got a 4, 7 pair here and a 6, 7 pair here. That's not an 8. So this is down to 1 or 6. Can we improve on that? Don't know. Don't know, I'm afraid. I've got a 3, 4, 5, 9 quadruple in column 4. So that square is not, that's got to be a 7, that's got to be a 4, that's got to be a 7, that's got to be a 6. So that's not a 6 now. Let me go back to my quadruple. Where was it? Those squares. 3s, so that's not a 3. I've now got a 1, oh, so I get left with a 1, 8 pair. Oh, okay. Can I do something similar down this column? 2s, 4s, 4 here gets ruled out, so 2s, 5s and 9s. Oh, the 4 is giving me a 4 and a 5. Okay, so probably I'm just doing bad Sudoku now, because now I've got a 2, 9 pair at the bottom, which is giving me a 3 here and a 9 here. And I can get rid of the 9s from there, and I get a 4, 5 pair. Oh, and I've broken the puzzle. Oh dear, what on earth went wrong there? Let's unwind. That's a bit embarrassing. Sorry, Pixel Plucker. What did I do wrong? Oh, you know what I might have done wrong? I'm looking at 2, 4, 5, 9 in here. But I know there's a 4 in there because I said there was a 4 in this domino, so that's probably what I did wrong. Let's go back to this. I've got a 4 in here. So that's a 3 and that's a 9. Now the other thing I could have done was go 1, 2. That felt like good logic, didn't it? 3, 9 come out of these squares. So that means this square is a 3, this square is a 9. 3, 9 come out of this square, that's a 2. Okay, and we end up somewhere like this. Now, can we keep going with this? I don't know is the answer. what did we learn? We got a 9 here. Okay, so the 9 down there, that was still good logic. We get no 1 into that square. No 1 into this square. So the actual digits that I need to put down at the bottom of the grid, I'm going to do this more carefully now. 2, 5, 6 and 9. So 6 is not in those squares. So 6 is in one of the... Oh, so 6 is just placed in rows in this row now, which is a lot easier than we were doing before. 2 comes out of this square. I might be able to go further than that. I'm not immediately seeing how. So this little square is a 1, 3, 7 or 8. Oh, well I can tell you one thing it's not, and that's a 1. Because once we've got 6 plus 1, we're not going to make that square an 11. And that's rather nice. So that means that 1 is in this domino in in row 7, which means that we can take it out of those squares. Almost good, but not quite good enough. 3 comes out. Oh, 3 comes out of those squares as well. Oh, and of course, this being a 4, isn't it weird? I dropped the ball on this earlier as well. There's a 4 in there, so that is an 8. That is a 4. That is a 7. So that means that square's a 1. And this, we get left with a 3, 8 pair in the row, which makes this square a 7, this square a 5, that a 7, and that a 3. That's a 5, 7 looking at an 8 therefore. That 7 is giving us a 7 and a 5. Okay, so it was just a massive ricket, wasn't it, by me not being able to fill in these digits correctly. But once we did, it actually became doable. So now we've got 1s and 4s there. We can place the 1, place the 4. Get rid of the 4 from that square. 2, 9, 4. Okay, 9 here means this is an 8, of course. So these two squares have got to be 4 and 5, which is resolved. This column needs 1s, 3s and 8s into it. Nearly. 1, 3 and 8. That's not a 1. Yeah, probably this 13 cage is going to reveal all the secrets of the world, I think. And I'm noticing that digit's now gettable as well. 6, 8, 1 into those squares. 8 and 3 into these squares. 3 and 9. Keep going. Okay, we can take 9s out of those. I want this to be a 9 for some reason. I don't know whether it will be. 8's come out of these. So we've got 4, 5. No, it's still not done. Oh, don't say I've messed it up again. Okay, so this is a 2, 5, it's a 2 or a 9 only, I think. So that forms a 2, 9 pair in the column, which suggests this is a 1 or a 3. And that's a little bit terrifying. So if that's a 1, these add up to 12, that's possible. If this is a 3, these add up to 10, that's possible. Good grief. Okay. So, well, it must be done somehow. Oh, I've got a 3, 8 pair. No, that's not how to do it. There's a 5 in one of those squares, so we can get rid of 5s from these two squares. It must be Sudoku I'm overlooking. Of course it will be that. Come on, Simon. Sort yourself out. Where is the Sudoku we're missing? Or is it a box I've not done? That's the other possibility. Let me think about that for a second or two. Can we get more joy from something else? We can. I don't know, actually. This can't have a repeated digit in it, but it's not going to have. This, oh, there's a 2 here, that's probably it. So this is now, no, that's not it. 1s, 6s, 2, 6, 9. Oh, there's a 2, 6, 9 triple in that row and a 1, 3, 8 triple, but that's all fine. No, okay, so now I'm getting more convinced that I've just missed something really obvious. Let's try and tidy up. Yeah, look, there's an 8 here. 8 and 2 go in. Oh yeah, okay, so that's 2, that's 2, 4, 9 in here. That gets us the 9 here, which puts 2 in that cage, 5 here, 9 here, 6 here, 2 here. These have to add up to 11 now, so you can see the only way that works is with 3 and 8. 8 and 3 go into there. That puts 1, 1, 3 into those squares. And it's all easy if you actually do the right things with your pencil marking. So make sure, boys and girls, you do that, because then you can finish the puzzle. Wow, not easy. Thanks very much for watching. I better get on and upload this or it won't be ready by 8:30. But Pixel Plucker, take a bow. That was brilliant, absolutely brilliant. And sorry for the ricket at the end. But yeah, central tendency, still don't understand it. See you later on Cracking the Cryptic.